All right, let's jump right in. Today we are doing a complete first principles teardown of an open source project simply called Agentic AI. I'll be coming at this from the AI systems architecture side.
And I'm bringing the senior backend engineering perspective. We are tearing down the Python implementation of this system today. And what's really fascinating here is that this is a fully transparent, hand-rolled AI agent. We're talking zero orchestration frameworks, zero bloated libraries, just clean, raw code doing exactly what it is supposed to do in production.
So here's our roadmap for this explainer. 1. First principles engineering. 2. The routing framework. 3. System design and the data pipeline. And 4. Getting started locally.
Okay, let's kick things off with part 1, first principles engineering and architecture. Look, if you're a back-end engineer, you have absolutely felt the pain of black box framework wrappers. You end up pulling in these massive dependencies just to get an LLM to call a basic tool. And when it inevitably breaks in production, you are stuck debugging thousands of lines of abstracted spaghetti code.
Exactly. You completely lose control of the payload. So instead of opaque abstractions like LangChain, this project implements the core reasoning and acting loop as just a plain Python while loop. It makes direct HTTP calls to the LLM, whether you're hitting Anthropic's Claude API or a local Ollama instance, and it hand dispatches the tools. You can literally read the entire loop top to bottom in a single file and know exactly what the system is doing at every single microsecond. It is incredibly refreshing.
And inside that raw loop is a pretty brilliant robustness fix. You know, a standard bounded loop follows a strict thought, action input, and observation cycle. But when you start using weaker local models like a 2 billion or 8 billion parameter model, they tend to get really confused once the context window fills up. They'll just spin out, repeating the exact same thought and action over and over until they hit their maximum step limit.
Right, which completely burns compute and basically hangs the UI for the user. So the fix here is so simple, but so powerful. If the model emits a reasoning step but fails to include an action line, the loop instantly breaks and treats that text as the final answer. It completely prevents that common production failure mode where a local model just burns its remaining loop budget and returns an empty response. You fail fast, and you actually return value.
Moving over to the back-end structure, the architecture relies on 3 clean, independently scalable FastAPI microservices. The conversational agent and chat UI sit over on port 8082. The book ingestion and vector search service sits on port 8081. And port 8083 runs a Model Context Protocol, or MCP server, which exposes MongoDB as callable tools over server-sent events. The massive architectural win here is that these services share absolutely no in-process state. They only communicate over HTTP, meaning if your ingestion queue gets backed up processing massive 100-page PDFs, you can scale that specific ingestion service horizontally without impacting the conversational agent's latency for your active chat users. It's totally decoupled. And for storing all this, MongoDB is the absolute source of truth for the entire system. It persistently stores the conversations, the exact sequence numbers of messages for ordered replay, and the entire catalog of ingested books. It is also exactly how the system handles memory constraints. Instead of a massive, unbound message dump that inevitably causes the LLM to forget its original instructions, the classic amnesia problem, this system uses a token-budgeted, tiered context. It passes a rolling, compressed summary of older turns, plus the last few verbatim conversational turns, and perfectly clips them to a hard token budget. The model always has room to reason, no matter how long the chat session goes on. Now, before we move to the routing layer, a quick aside. If you're following along and thinking, well, I love this architecture, but I really strongly prefer compiled binaries, you are in luck.
For sure. There is a fully equivalent Go implementation of this exact same architecture. It gives you strict static typing, Go routine safe tool dispatch, and it compiles down to a single native binary. We've dropped the link to that repository right in the description.
Let's transition over to part 2, the routing framework. The user interface features these really slick web and My Library toggles, and these are not just cosmetic visual filters, they act as dynamic runtime routing. Before every single conversational turn, the user can pick web via Tavily, My Library via Pinecone, both or neither. Exactly, and based on those toggles, the agent engine assembles a completely custom toolset and dynamically updates the system prompt to match that specific request. This is absolutely critical for accuracy. If you don't toggle the web search, the Tavily tool is completely stripped from the context. No dead tools are passed to the LLM, meaning you drastically reduce the surface area for hallucinated tool calls. The model literally cannot misuse a tool it doesn't know exists.
The framework also handles document-aware routing beautifully. Let's say you ask a question about Game of Thrones. The book search tool narrows the Pinecone query specifically to that book's unique ID. But what if multiple books match that exact title query? Traditional RAG architectures usually just execute a blind retrieval, grabbing the top K chunks across thousands of unrelated pages and just crossing their fingers. This system does not do that. Instead, the tool returns a needs clarification sentinel. The agent stops its loop, breaks out, and emits a clarification prompt back to the user, asking them to pick the exact right source. It's an infinitely better user experience to have the agent ask for help rather than confidently hallucinate the wrong answer.
And this ties right into how it handles citations. Every single answer gets honest provenance labeling. It'll explicitly say from my library, from web, or model's own knowledge right alongside clickable web citations.
And that label isn't based on some flimsy, hard-coded UI rule. It is derived directly from which tools actually returned results during that specific turn. If the Tabley tool fires, you get a web citation. Plus, those URL and title pairs are persisted directly into MongoDB as message metadata, meaning your clickable citations survive a full-page reload or browser restart.
By the way, that Go version we mentioned earlier natively implements this exact same runtime routing and clarify back mechanics. Because of how Go handles interfaces, this source toggle routing logic is just a really clean read in Go's type system. Again, definitely check the description for that link.
Moving right along to part 3, system design and replicating the build.
So, why use Python for this primary showcase? Well, because these are 3 separate FastAPI apps communicating over HTTP, the ecosystem perfectly matches the workload.
Yeah, Python is incredibly mature for these specific tasks. You have PDF Plumber for robust book extraction, which is notoriously good at handling complex PDF layouts without breaking. You have Nomic embed text running locally via Ollama for embeddings, which is a massive cost saver compared to hitting external APIs constantly. And Python has a very straightforward MCS SDK that makes building that server-syn events MongoDB tool server an absolute breeze.
And this architecture utilizes a really clean, resilient 6-step data ingestion pipeline. 1, you drag and drop a PDF in the UI. 2, the text is extracted. 3, it runs through a fixed size chunker with text overlap. 4, it generates 768 dimensional embeddings using Nomic embed text. 5, it batch upserts those vectors to Pinecone. And 6, it writes the definitive catalog entry into MongoDB.
The engineering trick that makes the user experience so good here is server-sent events. The live terminal progress streams directly back to the browser per chunk as it uploads. You aren't just staring at a spinning loading wheel wondering if the server silently crashed in the background. You see the exact status of the extraction and embedding process in real time.
This decoupled vector layer also demonstrates some serious architectural discipline. Pinecone holds only the 768 dimensional vectors and the chunk metadata. MongoDB holds the canonical record. Because of this strict separation, you can verify your freshly ingested PDF is findable in Pinecone directly, without even touching the LLM. And if your team ever decides to swap Pinecone out for a different vector provider entirely, like Milvus or Weaviate, the agent's core codebase doesn't change a single line. Literally, only the retrieval microservice needs updating.
We also have to highlight this number, 72. There are 72 zero-dependency unit tests in this Python project. They thoroughly validate the chunking math, the context budget arithmetic, the prompt building, and the core reasoning and acting loop itself. And all of it runs without needing Pinecone, MongoDB, or an LLM actually running. It is built to be robust and instantly testable.
And for our third callout, the Go repository uses Go routines for its MCP client, but keeps the exact same MongoDB schema. If you are an architect looking to compare 2 production-style takes on the exact same design pattern, putting the Python and Go codebases side by side is a fantastic learning exercise.
All right, final stretch, part 4, getting started and deploying locally.
Getting this running locally is shockingly frictionless. You run .setup.sh, it is completely idempotent, which we know senior engineers love. It safely installs Python 3.11, MongoDB, and Ollama. It pulls the local embedding models and the Gemma 2B chat model, scaffolding your config file automatically. After that, you literally just type .run.sh. What's brilliant is that even if you don't have Pinecone or Tavly API keys set up yet, the system just defaults to Ollama. It functions beautifully purely on local models, which means you have ultimate data privacy right out of the box.
The crucial takeaway here is 0 black boxes, period. Each of the 3 services is under 500 lines of code. It is entirely designed to be readable, adaptable, and completely owned by you.
And if you want to see all of this in high definition before you actually pull the repository, there is a full GitHub Pages showcase available online with screenshots of every single feature we just discussed.
And one final reminder for the back-end engineers out there who strongly favor static typing, raw performance, and single-compiled binaries, the Go version of this exact same agentic loop is linked right down in the description. It is the exact same architecture, the exact same database schema, just built in an entirely different language paradigm.
We've unpacked the robust while loops, the decoupled microservices, and the dynamic routing that makes this whole system tick. So we'll leave you with this provocative thought as you head over to GitHub. When you finally ditch the heavy, bloated frameworks to build your next transparent agentic loop, will you build it in Python or in Go?